All right, let's get started. Again, thank you for joining on this Friday afternoon. It's greatly appreciated. This is a follow-up special topic to our winter weather training. So this is all about ice storms. So on this introductory slide, we'll go over the plan for this talk, beginning with an overview of freezing rain, factors that control the liquid to ice ratio, a review of the historic 1998 ice storm for our region, analysis of a few local ice storms from the last 15 years, and then we'll go into how measurements of ice accretion work both from automated systems and from folks like you. So how and when do we get freezing rain? The basic process, of course, freezing rain is just plain rain, right? Until it reaches the ground. So we need the ground to be sub-freezing with a warm layer above that is able to melt the falling snow that forms well above the surface. If that warm layer is shallow enough, the drops won't refreeze. Instead, they'll supercool. They'll freeze on contact with cold surfaces. And this tends to happen early in the winter. Studies have shown for our area, we do expect the occurrence of this to be in the first half of the winter. In December and January, you can see a big spike in the reports of freezing rain. And this is based off of a 10-year period. So it's likely, if we haven't seen a freezing rain event through the end of January, it's probably less likely once you get into February and March based off of our data. And so in addition to freezing rain, we're interested in freezing drizzle because it takes just a trace of precipitation to impact the public. Basically, travel conditions can be quite difficult even without actual rainfall with just drizzle. And so what we look for as forecasters is a lack of ice in the clouds, meaning that the clouds are warm enough. Basically, we use a threshold of -10 degrees Celsius to say, okay, but chances are we won't see any snow form, and instead we'll have all liquid in the cloud. And so this tends to happen actually at the end of a snow event in which there's warm air moving in near the surface. And so we actually, as an example of this happening last winter, this is something we, as a forecaster, will indicate in our area forecast discussions. So in this case, an excerpt from one of our forecasters identifying the fact that the forecast sounding that we look at, they showed no ice, and therefore we added a chance of light freezing drizzle. So that was added to the forecast, even though we did not forecast any measurable precipitation. And so as an example, what we're talking about when we look at a forecast sounding, this is the temperature and in red and the dew point in green. And so it's indicating near the ground, the air was completely saturated when they're overlapped. In addition, the temperature is between 0 degrees Celsius and -10 degrees Celsius throughout this entire layer, all below freezing. That tells us that the precipitation is going to be frozen. But in this case, because the temperature was not cold enough, instead of getting snow, we actually had rain. And so here I'm illustrating what we also use to complement our forecast soundings to get some ground truth. We, of course, use radar. And so on the left is the reflectivity. In this example, we see very light in the blues. We see a signal of precipitation that is so light that it probably is drizzle. And to help us identify that as being drizzle, we also look at a different output from the radar called the correlation coefficient, CC, on the right-hand side. And very high values are going to indicate that the precipitation is very uniform, meaning that instead of snow, which has various shapes and sizes, the drizzle is basically all very small droplets, which look the same to the radar. So with that in mind, we would, in this case, in the circled area, we would look for potential for freezing drizzle. And in that event in early January of this previous winter, we indeed got ground truth from a spotter who indicated that in Ogdensburg, during the afternoon hours, there was light freezing rain accumulating on surfaces, and roadways, therefore, were slippery. So freezing drizzle is definitely something we want to pay attention to, even though it's not truly an ice storm. And so the processes, going in depth of how this works, as I mentioned, it basically, freezing rain is rain that is able to freeze on contact. And so that's why, in terms of looking at this warm air wedge, it's very similar to what the air looks like when you have rain, except you have this cold air wedge below. And as that wedge increases in size, you'll more likely see sleet and then snow if there's no warm air above freezing in that layer below the clouds. And so what we're looking for is, by definition, this is a temperature inversion, where we have warm air atop cold air. So this then, if we look at some of the factors that go into creating this type of profile, this graphic here goes into a case study in which we like to look at forecasters. We're going to look from the top down. So I'll describe first from the higher level downward. We have temperature and moisture that indicates that there's some dry air until you get low enough, and that's where the cloud forms. In this, where you have saturation here, temperature is well below freezing, this 0 degree line highlighted in yellow, and therefore the precipitation begins as snow. As you can see on the right-hand side, the wind out of the southwest is indicating that we're going to see a lot of moisture being moved into the area. Basically, that's an indicator that we'll continue to see saturation over time. As we go down, continue going down in this red layer, suddenly we have the temperature and dew point going above freezing. So this is close to the ground, and as you, in comparison to the cartoon on the left, you can see that indeed it's a shallow layer that's warm, and then in the blue you have a really shallow layer that is below freezing. And so this is a perfect example of what we would expect to see when there's freezing rain. So this is roughly the lowest 1,500 feet. This is quite low. So this makes it important for us to have a lot of data close to the ground in order to get a really good sense of what's happening. And to give an example of something that shows the difference between freezing rain and sleet, you can see here on the top, this is actually an example where that wedge of cold air is so deep that you do get some partial refreezing. And so in this upper case, the likely precipitation type is sleet, whereas in the bottom, as you can see the difference in the red and blue, now you have a very small layer that is cold, below freezing. And then so the difference is subtle. So if this is poorly predicted, then you could easily have a situation where instead of freezing rain, you have sleet, or vice versa. So this is one of the challenges for forecasters, is the subtle difference in the depth in which the temperature is above freezing, and the magnitude as well. As you can see, that obviously can vary. The shallow cold air, excuse me, the shallow cold air is quite, is not quite as cold. -3 degrees Celsius is the minimum, whereas for the top case, you can see that it's all the way to -10. So it's a combination of the depth and the magnitude of how cold that can determine the precipitation type when it's frozen versus liquid. Now, if we look at the example of what we want to see for an ice storm, here are some factors. So on the top, you can see in blue, we want to see cold air from Canada. Basically, it has to be a high pressure system that supplies sufficient cold air into our region in the North Country. Simultaneously, we have a surge of warm, moist air from the Gulf of Mexico that would supply a tremendous amount of moisture to our area. Meanwhile, you have a frontal boundary that is draped over our area, and this clash of air masses basically is what we see. And it stays in place because of a blocking high pressure system. And this low pressure system, well to our west, rides northeastward. We'll continue to see this clash continue between the air masses. And so again, that shallow cold air is a key component. So all this working together was a setup for our January H98 ice storm. So again, the idea of a shallow cold air layer near the surface is what we expect to see. Temperature likely will barely be below freezing, but that, as long as it's maintained over time, it doesn't matter. And in this case, there's a long duration of it. So why is the St. Lawrence Valley in particular prone to ice storms? So we can see in this example, and what typically will happen is we get a northeast wind that dreams down the valley. And so the cold air, which is denser than the warm air, it is preferred to undercut that warming that's going on higher up. And then you have the barrier to the east with Adirondacks. So it's really the topography and the geography really maintain really favorable conditions for freezing rain in the St. Lawrence Valley. Now in eastern Vermont, we get a phenomenon called cold air damming, which is depicted here in this animation in the middle, where both the White and Green Mountains, in particular in New England, we see this phenomenon where the low level air gets it's forced to decelerate as it hits up the mountains. And so this will favor the lingering of cold air on the east side of the slopes. As you can see on the right-hand side, this is depicted with an easterly flow underneath a westerly flow aloft, which in our area typically is out of the southwest during our ice storms. So we see this forced inversion based on the topography. So the frontal inversion will set up often in eastern Vermont, where the mountains are trapping that dense air near the surface. And this actually happened last weekend when we had some potential for freezing rain, but thankfully temperatures were just above freezing in eastern Vermont, as you can see in our daily climate map, in which the maximum temperatures on Saturday, December 12th, it showed the stark difference, basically 10 to 15 degrees lower the maximum temperatures east of the Green Mountains compared to elsewhere in the North Country. So let's move ahead and talk about how ice storms, similar to snowstorms, we can look at a ratio of how much precipitation is needed to reach a certain amount of accumulation of frozen precipitation. So just like you have a snow to liquid ratio, you have an ice to liquid ratio that will help us predict how much precipitation will translate into a certain thickness of ice. And research has shown that there are 4 key factors. We'll talk a little bit about each. So again, ice efficiency is telling us what is the expected ice accretion based off of various the precipitation and various factors, which can include the wet bulb temperature, elevation, wind, and the intensity of precipitation itself. So the wet bulb temperature, the reminder, if you don't know what that is referring to, basically what is considered to be the dry bulb temperature is what we say is just the normal air temperature, where the wet bulb temperature is what the air temperature is going to be at 100% relative humidity. So when there's a larger difference we talk about, meteorologists will often talk about something called wet bulb cooling processes, where there's a gap between the temperature and dew point near the ground, which will effectively get us a lower temperature when precipitation begins. So when relative humidity is high to begin before the precipitation begins, then there's less distance that the dry bulb temperature can fall. Therefore, in relation to ice accretion, we actually have seen that you want a sufficiently low wet bulb temperature, as the 31-degree threshold indicates. In this chart, you can see that on the x-axis is the wet bulb temperature, and the y-axis is the ice to liquid ratio, and there's definitely a drop-off in how high that efficiency is when you get to a wet bulb temperature that is closer to freezing. So that's one thing to keep in mind, is that when we, in addition to what the air temperature is, the wet bulb temperature is a key factor into how well that ice will accrete relative to when the temperature is, wet bulb temperature is lower. So the second factor is wind. This is a pretty straightforward one, where we do see higher efficiency of ice accretion when the wind is stronger, and especially above 15 miles per hour. It promotes a faster freezing process and greater chance of raindrops contacting the surface. And studies have shown that, in particular, above 18 miles per hour, the ratio is remarkable, that you can be 100% efficient even, where every bit of precipitation is going to accrete. This is an example of an early way of factoring in wind to precipitation in an ice storm. It's an accumulation index that just basically will tell you, hey, if it's this amount of ice and this wind speed, the damage is going to be in this category. So we'll go into a little bit more of this type of forecasting that we do in today's NWS process, but this is an example of how we can quantify the impact of wind and ice to give an idea of how you can see a lot more impact from ice when wind speed increase. So elevation in the North Country is incredibly complex, of course, in both Adirondacks and Green Mountains and into the Northeast Kingdom. So we really need to understand, and unfortunately the scale is so much small that it's difficult for us to know exactly where in that terrain where there's going to be ice and where it's just going to be wet. The key question is where that warm layer is going to be relative to the mountains. So this makes it much less predictable. In the higher terrain, in fact, there's a situation where we see at the summits, it's above freezing on the ground, then down to maybe 1,500 feet, there's ice. And then below that, again, it's warm enough that it's just plain rain. So that's a lot of variation, and especially because it's complicated by the latitude in most cases. And then finally, the intensity of precipitation. So this graphic here shows the ice to liquid ratio as a function of the precipitation rate in inches per hour. And so it's a really steep drop from the light precipitation to slightly heavier. So counterintuitively, one could say that it's the very light precipitation that actually is more likely to give you more efficient and therefore better ice accretion. So again, heavier rain actually leads to lower efficiency if you don't factor in other things like wind. So the rainfall rate, when it's high, you'll get runoff. And so that is the key thing. Therefore, you just don't add any accretion to what's already there if it's too heavy. So putting it all together, currently the National Weather Service nationally has a severity index, the WSSI, that has ice accumulation as one of its factors. So the impacts, as we just went over, an easy one for us to quantify and put out to the public is the idea of wind speed and ice accumulation is very well understood, the impact that higher wind speeds have on ice. And so this is all based off of the impacts, of course, to infrastructure. We also factor in the impacts in terms of where people live. So the urban areas are going to be weighted more. So typically in the North Country, of course, with it being quite rural, we're biased to having relatively low WSSI. It takes a very impactful, a very large event to be impactful. This is on a 6-hourly basis. And note that we do have ice storm warnings that we put out only when a certain threshold is reached for our expectation of ice accumulation. So here's an example of what we're talking about, what we put out to our partners for emergency management, as well as for the public, the idea of expected ice accumulation in a map like this. We will put out similar to our snowfall. And so this is meant to be consistent with that index that I just showed, the WSSI. And so the interesting thing here is when we evaluate how our forecasts do in a map like this on the right-hand side, we actually are taking the data from basically reports both from the public and from automated weather systems. They're mixed together. And so this is what we've been emphasizing, in particular this year. But as an organization, we want to make sure this is consistent, because otherwise you would never know. And if they're not measured the same way, which is the case, then we really can be misleading if we're not consistent with what the ice accumulations are. Because as illustrated here in the potential impacts on the left, in this case, we were forecasting in the range of 1/4 to 1/2 inch for many areas. And then you take a look and you see, oh, wow, there was 1 inch up in Messina. How'd that happen? That's a big difference. And it turned out maybe that was an overestimate, and because we did not see the types of impacts that you would expect for that amount of ice accumulation, according to the research that's been done on potential impacts for a given ice accumulation. So again, the ice storm warning is very specific, and we will only use it if we're expecting 1/2 inch of flat ice accretion within a 24-hour period, and that it's widespread enough that it occurs in at least half of a forecast zone, or encompasses most of the population in that zone. And as a reminder, if you don't know what the forecast zone they're referring to, it looks like this. So in some cases, it's a full county. Otherwise, in other cases, it's broken up into sub-county level. But the size, it will vary. Because it varies, you see the complication with where we're looking at population and the zone themselves. So there's a judgment call that has to be made, and we don't want to overwarn. And so again, the fact that we really rely on measurements from the public and spotters, it comes into big time. It's really important to help us put out the best forecast we can. So let's jump into, we're going to go in reverse chronological order. So we're going to look at some recent events, but to start, we'll look at something that actually did not pan out, that we got lucky because some of the ingredients were there. So this was this past weekend. Looking on the left to start with, at 10 a.m., this is a surface analysis. I'll just point out in the big picture, we had at 10 a.m. Saturday, we had a weak frontal boundary to our south with low pressure. The main area of low pressure was actually way out near western Michigan. And at the time, we had high pressure to our northwest, and this was sufficient to get some northerly winds out of the north-northeast into our area. Temperatures were just above freezing, or even below freezing, actually, in parts of eastern Vermont. So at this time, the conditions actually look roughly similar to what we are afraid of for an ice storm, as you have that cold air, just cold enough, sufficiently cold with the frontal boundary to our south. However, as you can see by 7 p.m. Saturday, now the frontal boundary is actually to our north. And this, as you can see with Ogdensburg, temperature in blue, dew point in black, and relative humidity in green, during this time period, the temperature was near freezing, and then it sat with some saturation. And then when that front lifted to the north, suddenly, instead of draining more cold air in, the temperature and dew point just jumped from the low to mid 30s all the way into the mid 40s. So this type of phenomenon was pervasive in all of basically everywhere west of the Green Mountains. And so we had no issue, even though some cold air did eventually work its way back into the St. Lawrence Valley, we actually dodged a bullet and had no concerns for freezing rain. Meanwhile, as you can see at 7 p.m. on Saturday, temperatures 34 in Springfield and 37 in St. Johnsbury. So St. Johnsbury and Springfield still had that cold air damming situation. And this is what we were looking at to the east in Gray, Maine, as a proxy to what was going on there. You can see that in the lowest part of the atmosphere, we did have, indeed, it was quite saturated. So as we were talking about with the wet bulb temperature, we would not expect any kind of wet bulb cooling. So that was a good thing. But temperatures were very close to freezing. You have that warm nose that is well off the surface. And point out here, you have that preferred southwest wind, though, to keep things saturated, and that low-level wind that's out of the southeast to east. So this is, as opposed to the northeast, this is one of the key components of why we dodged a bullet with this case, is that we didn't see that cooling air. It just basically maintained that 33, 34 degree temperature in eastern Vermont. And the reason that southeast wind is important is that we saw strong warming below that warm nose. And so instead of having that cold air undercut that warm nose, instead we just basically stayed where we were at throughout the event. So all the light precipitation that we saw Saturday night was in the form of just plain rain. In contrast to last winter when we saw multiple freezing rain events. So here's an example of one that had some pretty big impact in a localized area in the Champlain Valley. So this was our forecast just ahead of the event. We expected freezing rain to move into the area in a situation where we actually saw cold air undercut the warm air during the event. So there was not cold air in place already. In fact, if you recall, this was on January 11th of this year. And before this event took place, temperatures were actually really warm. We saw widespread 50-degree weather. And then a cold front moved through. It slipped to the south of the Champlain Valley. And as a result, so here's what the area we were focused in, 1 a.m. Sunday. So in particular in the Champlain Valley, again, we see another situation with the front slipping to our south and some northerly winds at the surface. So it turned out we indeed were able to get freezing rain. In fact, in this report, that was very helpful from Jacob Lancaster, we saw a combination of both freezing rain accumulation of 3/4 of an inch and some strong wind of 33 miles per hour. So because of that combination of wind and freezing rain, we did indeed suffer some reports of damage. So these are some estimates for these 3 zones in Western Chittenden, Western Franklin, and Grand Isle counties in Vermont. Then we go back to a bigger event in December 22nd of 2013. This affected a wide area that you can see in this map with 1 inch plus in the St. Lawrence Valley and widespread 1/4 to 1 inch in the Champlain Valley down through basically the western slopes of the Green Mountains into parts of the Northeast Kingdom. And so this was the biggest ice storm since the January 98 one, and it had very heavy precipitation and strong enough vertical motion that and instability to get some thunderstorm sleet and freezing rain reports. $8 to $10 million in estimated damage, 75,000 plus people without power in the North Country, with a very wet storm with 1 to 2 inches of liquid, and ice accumulations, again, that range from 1/4 inch to 1 1/4. I would imagine many of you are familiar with this since it's in the recent history. And the fun fact of that here at the airport, the operations had to use a lot of chemicals to melt stuff off and over the event. And yeah, this was a very big ice storm for our region. Some photos that maybe some of you took in our area, and this is the type of report that we love to see, with a very specific, good quality photo to illustrate how much ice secreted. And this is a case of flat ice of 3/4 of an inch. And this is the type of information we really do like to see to help us in getting the best validation of our forecast. And now we'll go one more before we hit the 98 storm. This is a lower end ice storm where we saw amounts range from 1/4 to 1/2 inch, and this was isolated mainly to southern Vermont. In this case, we'll look at Albany, New York, observed sounding to get a sense of what was going on. So here, if you look at this sounding toward the bottom, highlighting here that the wedge of cold air was perfect for getting just enough sub-freezing air near the ground. And again, we're seeing these wind barbs out of the southwest above that layer. So we're getting that combination of moist air, very saturated, while we still are seeing enough cold air at the surface. And in fact, looking at the data, just this hourly information, this is from the ASOS automated system at Springfield, Vermont, where there were frequent reports during a 4 to 5 hour period of light freezing rain with light or northeast winds. So again, we would want to see a northeast wind for any of these events, and that maintains that cold air at the surface. So temperatures were just cold enough, and as you can see also, the wet bulb temperature was even lower because the dew point, there's about a 2 to 3 degree spread between 30 and 27 or 28. So this, again, was not a big ice storm, but it did have some impacts with 1/4 to 1/2 inch in southern Vermont. All right, so now let's jump ahead into that ice storm, that historic one. Here, the overview of the area of most interest, even though it impacted a big area, it was actually into the St. Lawrence Valley in New York and into southern Canada. That got hit, that hammered by far the most. And so this was definitely a situation where there was sub-freezing low-level air that resulted in areas lower down that had seen some of the biggest ice accretion rather than higher up. And this particular ice storm was so historic partially because there was just a lot of rain as well. So there was flooding. We saw huge impacts due to the combination of flooding and ice accretion. Now, the summary, we saw a lot of power outages in the region with tremendous agricultural losses. So we'll just go over, there's a really good report that was done after the event, and so some highlights I'm going to hit here. So from the emergency management perspective, the National Weather Service was able to highlight the threat of a significant ice storm that would cause falling trees and power lines. And during the event, there were state-endorsed statements that address carbon monoxide poisoning and phone numbers to call for those in dire need of help. And states of emergency were declared that led to business in the school being closed, which reduced the traffic on debris-covered roads, which allowed crews to clear roads faster. So of course, we had storm reports. Skywarn had been around a long time, and it was activated ahead of this event. Combination again of flooding and icing. We relied on reports to help us out, especially because we had that power outage. This power outage forced our warning coordinating meteorologist to use handheld radio to keep in communication with some amateur radio operators. And that communication was vital to relaying information to our emergency management folks in northern New York. And the combination of our Skywarn spotters and co-op observers that during the event were able to keep the National Weather Service abreast of really what was going on, that otherwise there's no way that was going to happen, especially because back then our automated weather observing systems, or ASOS, were quite new, and they weren't able to keep in operation. And our radar system also were not. In fact, we lost any radar data out of our Montague, New York radar at the time. So that actually, that is the key thing that we, to this day, why we now have better radar information and automated weather observation than we did back then. The gaps in our data is basically, especially because as great as the spotters are, we certainly have a lot of uninhabited areas in our region that we need to know what's going on. And so that's these complementary systems all work together to help us ever since this 98 ice storm to really know how to best get the information that we need to the public. And so either reminders of just how devastating just the tremendous amount of ice accretion in our region. And also we saw the effects of the power outages and the downed trees, where the tremendous amount of damage with the utility poles coming down. So as a summary here, take home for this event was that, in quotes on the right-hand side, the lack of real-time information on ice accretions, particularly during the overnight hours when spotters reports are scarce, makes forecasting ice accretion difficult and adversely affects the quality of the forecast. In this storm, many spotters were without power, and there was great danger in venturing outside at night due to the darkness. So again, this was from a report called an evaluation of the severity of the January 1998 ice storm in northern New England. And so the report really helped motivate with how costly this was to improve some of the technology we use today, which again, the ice storm itself, the impacts were, a lot of it were to the forest. Can be seen up here in this map. We'll go into the final stretch in a moment to tie it together. Where thankfully that type of ice storm is quite rare. We expect even a half-inch type of ice storm in our region to maybe be every 15 years on average. So that takes us to the measurements. As I hinted, the 1998 ice storm was an impetus to get freezing rain sensors as part of our ASOS systems. This is what the freezing rain sensor looks like on the right-hand side. The sensing element on the top there is going to be able to detect changes in mass. So on the left-hand side is some output that is you can see on the y-axis is the sensor frequency. Basically, the change in mass is going to affect the vibration, and that's plotted here in real time, an example of what happened for a particular event where you can see on the top reports of freezing drizzle of the weather type starting just before 8 a.m. And that translates into a decreasing frequency over time. And so there's an equation that is used by basically it's programmed into the ASOS. You can see that when the precipitation is heavier, at what happens in the afternoon, where instead of drizzle we have freezing rain reported, the slope, the red line slope, it gets steeper. And so basically the weather type that is output is based off of certain thresholds that we see from this data. So over 6 hourly periods, basically we get an ice accretion that is reported from the ASOS. And so this is averaged together in 6 hour chunks, similar to be consistent basically with what we do for snowfall. So this is very different than what we do as humans. As a refresher, the way that we are measuring ice typically is through a ruler, of course. And if it's in a branch, for instance, we are doing a radial measurement. So we really to emphasize that the way that we measure ice is so important, because as an example here with this ice on a branch where you see a 1/4 inch on one end and a 3/4 on the other, basically if you were not to take an average, it would be quite misleading. And if you don't show us a picture, it also can be very misleading. So the fact of the matter is we do rely on accurate ice measurements, and this is our preferred way of doing it. And this is an example looking at in detail here of if you have a empirical rather than metric, and broken up into 1/16. In this case, this measurement on the right-hand side, that one side is going from basically you see a 3/16, and on the other side of the pole you see 7/16. So in this case, you would report it as 5/16. Or basically, if you just share the picture, we can take care of that as well. So another couple of notes, if you're going to go this route, if it's a very small amount, under 1/10 of an inch, we're going to just call it a trace of ice. And then from other aspects, if you're going to use a ruler like this, you can give it as nearest 1/8 or nearest 1/10. Again, the picture is key, because then there's less question about how exactly you took it. So this is again for radial ice measurements. But of course, we actually take two different types of measurements. We'll take an ice thickness on a flat surface as well. So this is more comparable to what the ASOS is doing, where we're measuring flat ice. Whereas again, B is the radial ice. And so these are not equivalent. And therefore, because you will get a different answer for how much ice is accreting with the two methods, it's absolutely critical that we either get a picture or we are told from you that it was a radial measurement or an flat ice measurement. So we'll do the conversion for you. But just to give an idea, it's basically 40% the difference between. So if you have the elevated horizontal ice, 1 inch, you'll actually be equivalent to 4/10 of an inch of the radial ice. So to summarize the idea of radial versus flat, in this image here on the upper left is what the ASOS is doing. It's taking a depth of ice above the ground, basically, whereas the radial ice thickness from a tree branch is going to be as shown here, and that's our standard way of having the public. It's a relatively easy way of doing it, but you could also do ice thickness on horizontal on the ground, for instance. And so that is basically equivalent to what ASOS does in terms of ice thickness, but typically there are differences between what is on a roadway or sidewalk versus what's elevated on a tree branch. So there's a lot of complexities to our measurements, and it has been illuminated in recent years by a study that was done in a forest. This particular experiment actually was able to determine that it's actually between 1/4 and 1/2 inch of radial ice that will cause moderate damage to hardwood forests. And then when you jump up to 1/2 to 3/4 of an inch, suddenly we're dealing with potentially catastrophic damage. And so these findings suggest that actually the 1/4 inch threshold, rather than the 1/2 inch threshold that we use currently for warnings, may be appropriate to alert the public to pending tree damage from ice storms. And this is especially true for the branches that have already been damaged. So what have we learned today? Well, the ways to get freezing rain, there's actually different routes to get them. They all involve having a low level of temperature inversion. To get an ice storm, it's more difficult, thankfully, and so that's why we see them seldom. And part of the issue is that there are competing factors to getting efficient ice accretion. The ice storms that we would define as such typically are roughly 1/4 inch of radial ice. We'll see severe damage to trees and 1/2 inch to power lines. And so for utility companies, they deal with that type of issue. So that's a complicating factor for the National Weather Service in our products, because we are dealing with both the public, which had a lower threshold for seeing impactful ice accretion versus what utility companies do. So again, these events are rare, but they're some of the most impactful we see in the North Country. And we have recently clarified that the difference between flat ice and radial ice measurements is key to creating consistency. That will better verify our forecasts. So with that, I'm very happy you have joined for this talk, and I see there have been some questions. And if you have any further questions, feel free to, after this presentation, you can contact myself or Robert Haynes, the Skywarn lead. And we are very interested in doing more of these type of specialized Skywarn talks in the future. So please let us know any topics that you'd like to see next. And we will be back with you next year. Hope you have a happy and healthy new year.
Looks like you have a few. Yeah, so feel free to go ahead and just go through these.
Okay, so we'll go through the question we have here. See one of them, some of the questions that were from someone who has left, but we'll go over. Okay, so the first question: when you list ice accumulation total, is that radial or flat ice? And what happens if the other type is submitted in a report? Okay, thank you, Lumi. That's an excellent question. So our ice accumulation total, we are, as a rule, we are using flat ice. And so that's why it's key that if the other type is submitted in a report, we will make note of it and make that calculation to convert it to flat accumulation. So it's absolutely no problem to give us radial. Just keep in mind that our forecasts are always going to be, at this time, we will continue using flat ice. So the other questions I see are regarding ASOS. And so unknown precipitation is reported rather than freezing rain or sleet. Can the ASOS discriminate between the two precipitation types? That's a great question. So yes, we do see this unknown precipitation, the weather type. The challenge for the automated weather station to sense the difference between, basically it's it hadn't been able to detect like for instance freezing rain is going to be based off of the accretion on that sensor, and if it's not able to determine that there's any change, that sufficient change in the mass on that sensor, then it won't report freezing rain. And so if it's also not, if there isn't if there's not particular frozen type that it knows, basically based off the different thresholds that for weather type, yeah, the unknown precipitation is going to be it's very likely to see unknown precipitation, basically because the mixed precip which occurs is not easy to discriminate. Are there any other questions at this time? Okay, and nothing heard or seen here. Again, I greatly appreciate you attending, and again, if you have any further questions in the future, please let us know, and I'll be happy to continue this series very soon, next year. All right, take care.